So this year, I'm going to talk about API composition. Just to give you some background about myself, I'm the CEO of a company called Tailcall. It's just been a couple of months. Prior to this, I was working as a VP of engineering at Dream11. Dream11 is the world's largest fantasy gaming platform. There I was there for almost 6 years. I was heading the edge engineering, and that's what I'm going to talk about today, some of the learnings and things that worked for us, things that didn't. And Dream11 actually worked at huge amount of scale, so we started off very small, but eventually we were like clocking millions of requests per second and those kind of things. I was also the author of Zero HTTP. That I got an opportunity to work on it, and actually this still runs production and especially powers our massive fan outs of 5-6 million concurrent users till date. So, yeah. The presentation today is split into 4 sections. I'm going to talk about what API composition is, what is the general problem that you kind of face when you think about API composition, how do you solve it, and if it's even worth solving. We'll talk about typically what companies choose when they want to solve the challenges around API composition, and what is a functional way of looking at the problem and thinking about it, right? In the end, we'll wrap up with the summary and the conclusion. So what's API composition? So in a typical microservice architecture, which sort of looks like this, and this blue cloud is basically your backend, your VPN, and there's a mobile device. And you have services. Each service is owning certain bits. They have very discrete pointed API endpoints. And the clients make requests to these services to get data. And between the services and the clients, you have a gateway. A gateway is typically a very simple, thin layer, which is just basically doing routing of APIs. So the request comes from the client, and the gateway decides which service should it go to. It also handles some of the cross-cutting concerns, such as authentication, rate limiting, and stuff like this. But basically, it's a very simple, lightweight system. You can pick up any API gateway on the internet and deploy on your system, on your infrastructure. What actually happens when you talk about composition is, say, for example, there's a user. I'm building a social network use case. So let's say there's a user service, which gives me these. When I hit the user API, I get these fields. And there is a post service. So user make posts, and the post has these 4 fields. It doesn't have user per se. It has a user ID. So now when I want to show it on the screen, I need to actually combine them together. So I need an aggregated data structure which has post information also and user information also, because I can't show user ID on the UI. So there's no API which exists as of today, because these are 2 independent services. They have just built APIs which are very pointed and very direct. So what you do is, this is where API composition comes into play. So, and this is mostly done on the front end. How many people here have actually written rich user interfaces ever in their lives and are attending a Scala conf? Kid. Okay, cool. So fairly less. So what I want to convince you all is it's a fairly complex problem. And it's a lot about the API calls is about nesting, making batched calls, caching, and evicting the caches. There are various strategies that you can use around evicting caches. You have to you have to do data validation. Sometimes the response coming from the server is invalid. You have to, maybe you were expecting a string, but you got an integer. There are errors, and you want to propagate errors. Exceptions could be handled in different ways. You might want to do a retry. You might want to propagate the errors up on the UI, or you might want to serve it from the cache. You also, once you build this composition, you might want to extend it with some kind of business logic or data transformation. So it can get fairly complex. That being said, on the front end, actually, it's fairly unstandardized. Right? So there's often a problem of overfetching. That means you made an API call, you got multiple fields. Out of those 10 fields, you just barely used 5 of them on the screen. The rest was just unutilized. And underfetching, that means you have to make multiple API calls to get everything to show on the screen. So, and there's no direct way of solving this problem, no standard way at least. Then there is this whole problem of modest hardware, right? The devices that you're using where you're doing all these operations, they're not very powerful. And obviously, they're on a very poor network. You could be on a 2G or a 3G, you just get into a lift. All of these environmental factors affects the reliability and the performance of the app, eventually affecting your user experience. So if you're building a rich user experience where you have tons of microservices and you're querying a lot of data, this solution doesn't work. And that's what happened with us. We had many when we moved from monolithic solution to a microservices, we started facing these challenges. Now, I hope most of the folks here are convinced. And if you're not, you should definitely learn from the richest man. He's complaining about the same problem on Twitter, about Twitter. But it's fairly complex, right? So apparently the app is making 1,000 poorly batched API calls. So it's hard. I hope everybody's convinced. So how do we solve this problem? So the general way of solving this problem is a BFF, right? A best friend forever. But unfortunately, that's not going to help you in this kind of a situation. What you need is a more technical way to solve the problem, which is a backend for frontend, right? It's a layer that sits between the API gateway and the services, somewhere here. It's a stateless system, and it sort of creates those APIs that you need, which gives you that access to aggregated data. So for example, in our case where I needed a post with the user information, that API would be built over here, which would make two API calls, combine the data, and send it back to the gateway. So it's a simple solution. The idea is that we move the API composition logic from the app to something which is to the backend layer, which is inside your cloud. And here, basically, you have good network and you have good machinery, so you can do a very good job. These are some of the numbers that we were able to serve in production when we moved all that logic onto our backend infrastructure, right? Millions of requests, 150 million users, 150 microservices. I think they were in more than that. This works, right? The reliability is much higher, performance is much better. You'll see a massive improvement in the user experience. The load times dramatically reduce. And when you're building a B2C app, it makes a big difference because eventually, when you improve performance, you'll see the bottom line of the company having an effect. Improving. But there are some challenges, right? So this worked in a way from a business standpoint, but from a technical standpoint, we had challenges. More specifically, 7 challenges that I want to talk about. And this took us a lot of time to kind of distill down. So, but these are important. So if you are working on something similar, you might also face these challenges. So the challenge number 1 was, it's a very specialized layer. Unlike an API gateway, which you can go on the internet, search for it, like the AWS has one, there's Kong, there are tons of open source API gateway solutions. You can download it, put it in your infrastructure, it's solved. But a BFF layer has to be hand-built. You have to write code for it. You can't just go out in the open source community and look for a BFF layer. You have to specially implement it for your use case. So companies keep doing this, and they keep reinventing the wheel. Developers move from one company to another. They rewrite the whole BFF layer. So it's very specialized. No reusability. The second challenge is it's fragile. The API gateway is one software, which is built over years of optimization, communities, and stuff like this. But the BFF layer is very specialized, handwritten. So the stability of the system is a function of how good your developers are. Now you can improve this reliability and the robustness of the system by using things like Zio or doing good code reviews, best practices, stuff like this. But it's a very difficult guarantee to kind of give to your business if everything is built by hand. The third challenge that we kind of faced as we scaled was the performance became extremely speculative. Developers would make small changes, and we had no clue if it's going to improve the performance, degrade the performance, and if it degrades the performance, by how much would it degrade the performance. So to solve that problem, what we would do is we would write tons of benchmarks, load tests, and like a very complex CI pipeline. And that would, any small change, like literally a 4-character, 10-character change, would go through this whole pipeline and would sometimes fail. And the time to market for those small changes was just enormous and would sort of sound silly when we would talk to our product managers. It was like, it has this whole pipeline, it's automated, but it still takes crazy amount of time. So that's a big challenge that you will face if you start doing something like this. And this happens at scale, okay? So if you're a small company, you might not face this problem. The fourth challenge is it's a monolith. To give you a perspective, this was at least, the code for this layer was around 10 times more than the second largest code base in the organization. Because this basically contains all the domains that you're working with in your organization. And if it's a B2C, it could be like huge. And you have the standard problems of a monolith. Upgrading libraries is a problem because if you make that upgrade, it just breaks the whole app. The onboarding a developer is very difficult. Changing the stack is very difficult. We were on Node.js. We wanted to move to some other stack. We tried Scala. We just couldn't migrate because it's a huge amount of code, right? The fifth point is we realized that canary releases should be a first-class feature of a BFF layer. Now, why is that? It's because whenever there's a backend change, basically a service change, you make changes in the BFF layer. And whenever there's a change, whenever a new feature is implemented on the UI, you still have to make a change in the BFF layer. So there's no way that you make changes on either of the sides and you don't deploy the BFF layer, and the BFF layer is heavy. Making a deployment over there is like expensive. And you incur that cost for every feature, every release, every week. So it's expensive. So a canary release should be, if we had to actually test some changes that we've done, what we had to do is set up an exact replica of the infra, and using DNS routing, we would kind of split the traffic and test if that system kind of works. So fairly complex, horrible way of actually testing your canary releases. The sixth challenge was it was very coupled with our backend releases. And this is very funny because even if our dev feature was done, we couldn't go live. Why? Because the backend was not ready. So the backend had to go first, then the BFF layer had to be deployed, and that's how everything would work. And the more funny bit about this is, if your code is all okay and there's a bug in the backend implementation, and the backend wants to revert, you also have to revert. There's no way you can stay on the same version. And then when, again, they fix it, then you again go back, and so it's a mess, right? So this kind of coupling was a big problem. And the seventh point over here is, it's a very controversial point because it's not very clear how does it relate with the API gateway. How does it, what's the responsibility of an API gateway anymore? All the cross-cutting concerns can still be handled by the BFF layer. I can write code to do authorization, authentication, all that stuff. And when I'm anyways writing so much code, why can't I write all that code which is there in the API gateway? And the second bit is, should the API gateway actually sit between the client and the BFF layer, or should it be between the BFF layer and the microservices? Where should it sit? And we have had like enormous amounts of debates about how do we fit all this stuff in our infrastructure. The thing that I would like to mention here is there's definitely something which is missing. There's a gap that is created by these legacy API gateways. And that's what the BFF layer is trying to patch. So these challenges were a big problem for us. After a certain period of time, it was dramatically slowing us down. Even though we had microservices which were helping us deploy in a decoupled manner, add that in the microservices system, but the BFF layer was still coupled with the overall infrastructure. So it was hard to scale. And if you think about it, the way BFF layer is kind of structured, and the first reaction that the people would have when they would kind of attempt making changes is, it's gross. Nobody wants to touch that system. Nobody wants to write code in that layer, right? So it was a messy way of solving the problem. So, okay, can functional programming or functional design help us solve this problem in a different way? It can, but if you think about functionally, if you want to solve a problem using functional thinking, the best way to do it is, create a DSL that solves this specific problem. And more specifically, create a DSL that's introspectable so that I can optimize, I can identify issues even before you deploy on production. And set up a very performant runtime, a runtime that can execute the composition logic. So use the DSL to define your composition logic and set up a very performant runtime to kind of execute all your composition logic. So, and that's what we are doing. So at Tailcall, we are building a modern API gateway that's programmable. It's fast by default. It's extremely robust. Its robustness is not a concern that a developer needs to worry about anymore. It dramatically increases the productivity of the dev, and it's open source. So how does it work? Glad you asked. So the high-level architecture kind of looks like this. So you have the services, you have the client, those remain the same. The gateway is swapped with the Tailcall gateway. And then there's a Tailcall registry, which contains all the specifications of your composition. So whatever the way you want to compose your APIs, that information is kind of created, saved in a JSON, and then patched into the registry. At a more granular level, the way it looks like is there's a composition spec that you have to create, like a description of how you want to compose all your endpoints in your system. The spec contains information about the schemas, like the metadata of the entities that you care about. Like in this case, there was user, there was post, and that information is the schema. The endpoint informations, are you making an HTTP call? Is it a gRPC call? All that information, some configs around caching or rate limiting and stuff, and you combine it with some logic and transformation. So I could have actually shown you Scala code here, because it's actually a very expressive Scala DSL, but then it would have taken another 40 minutes just to explain how it works. So I hope the sentiment is kind of conveyed here. Basically, there's a very powerful Scala DSL which allows you to kind of describe exactly how you want to compose your APIs. And you do that, and you compile it into a JSON. A JSON is one sample format. You can compile it into anything, but basically all that information is available to you in a serialized format. Now, once that spec is available, you publish it on the registry. And there are two steps to publishing. The first step is, run the validations. See, is there an invalid state that is getting occurred? Is there some situation that you've not handled? You identify performance bottlenecks, such as, are you making too many API calls? A lot of times when you're doing API composition, what ends up happening is you make an API call which gives you an array, and for each array element you're making an API call. So it's called as an N+1 problem. So you can identify that. Even this identification can happen before you deploy, before you even start your server. Because again, the spec is introspectable. You apply optimizations. The developer doesn't need to worry about things that can be parallelized. Automatically, the DSL will ensure that things that can be parallelized is parallelized. And a unique hash is generated. This hash is basically an identifier for your spec. So it's literally the hash code of your spec. And we'll talk about it, how we use this hash. And once you have this spec created and published on the registry, a unified endpoint is generated. So the unified endpoint gives you access to everything that's available on your system. And it's automatically generated. You don't have to write code for it. You can use various protocols like GraphQL or OpenAPI or REST or whatever standard you want to use to expose that API, you can do that. The way you consume it is make an API call, and any request that you make, you have to send the hash. The hash is a unique identifier for that spec. And if the spec changes, the hash changes. So you can only make a request for a particular specification, and that specification is identified by the hash. So this is an example of GraphQL. You could use any request. Now the hash code is very unique, and this is the most differentiating factor when you compare it with other API gateways, right? It gives you versioning, and that's very powerful because now as a developer, earlier when I had BFF layer, what I would do is I would have these routes, V1, V2, V3 in my code base, and I had to maintain them for eternity. I don't know what will happen if I go and delete that code. But here, I don't need to worry about it. Once a spec is created, it's saved in the registry forever. I just need to maintain the latest version of my code. In my Git repository, it's only the latest version. All the older historical versions are always there in the registry. So I get that capability. With that, I also get first-class support for Canary releases. That's because every release is on a different route. I can deploy it on production, and the clients won't make a request to that new version unless the ID is actually burnt into the app. It's immutable. If there is a version that is working in production, you cannot change it. And it's always going to work. So if you want to roll back, you can do it instantly. You don't have to do all that infrastructural complexity. You don't have to deal with all that. And you can deploy breaking changes. I can make a change where I can delete certain fields, delete APIs, and go to production without worrying about how would it affect the current working apps, because the current working apps are still pointing to the older version of the spec. And the resolution, so the fourth bit about this, how it works is how is the request resolved. So the request, when it comes to the gateway looks for that hash in the registry, gets the spec, decompiles it, executes it, and sends the response. So this bit is very straightforward. So in summary, this solution kind of solves most of the challenges that I have talked about. One thing that I would like to point out is it's extremely modular. That monolithic problem is kind of gone away because now what I can do is I can prepare my specs and publish it on Maven and actually download them in my application as a package. So every team can manage their own composition spec. And that's a very powerful feature. And the releases are decoupled because I don't need to care if the backend is deployed or the front end is deployed. It's always on a new version. I don't need to revert anything on the BFF layer. It's always, and the infrastructure remains the same. The infrastructure is not changing. So once the deployment of the gateway is done on those machines, they just remain the way they, like an API gateway, it remains like this. You don't make changes again and again. And it's an end-to-end solution. It's not just doing API routing. It's managing your composition. It's handling all the cross-cutting concerns. Sorry. And it can also create clients for you, automatically type-safe clients. In conclusion, API composition cannot be an afterthought. You have to think about it, especially if your business really goes out of control, like becomes really big. It's very important to think about API composition. It's extremely hard. It's not that straightforward. Hand-coded BFF layers do not work. You can try. After some time, you'll have problems. There are solutions like Federation and stuff. They all have flaws in them. And there are no generic solutions available. So you can't, as I said, can't go on the internet and download a BFF layer. Must explore Tailcall's developer API platform. You can get that information on tailcall.in. You can register and get information about. There's the link to the GitHub repository is also over there, so you'll get all that information. And yeah, thanks. That's all.